How stupid was it? They filled the entire cockpit with 100% oxygen. They locked the doors. They locked the doors of the command module so the astronauts couldn't get out or anybody get in. And what happened was there was a spark. And a spark in 100% oxygen, boom, was just like a pressure cooker, and they were dead within 20 seconds or so, or less than that. They were killed immediately. So those were the only three that were directly connected with Apollo that were killed. And there were other fellows that were pilots that were trying to become astronauts, and a few of them were killed just messing around in the airplanes in their airport.
Why did they use 100% oxygen?
It's a great question. It's a terrible answer. They only need actually about 5% oxygen.
Well, the air is 20%.
Yeah, the air is 20%. We can, at 5%, it's like being up at 5,000 or 7,000 feet altitude. So they really didn't need 100% oxygen. And
it required less pressurization in the cabin to use 100% oxygen, and so that was the reason the engineers gave for keeping 100% oxygen.
Yeah.
Whereas the mixture of nitrogen and oxygen required more pressurization.
Yeah. They didn't need 100% oxygen, that's for sure. At any rate, these three men were killed in 2 seconds. And then the redesign of the spacecraft interior was immediately started, and they did Apollo 7, 8, 9, 10, and finally Apollo 11, the lunar landing flight. And that all was recovered within, I think it was about 20 months, 22 months. So the recovery was very fast. Okay, so what did the show look like? Well, the whole show was actually 3 different types of flights. The Mercury program, John Glenn, who became a senator, was, and then he actually flew up to the space station. He went in one of the early Mercury flights. And then there was Gemini, which means the twins. And Gemini was 2. And they could get outside of the spacecraft, and they proved that when you're in orbit, because there's no atmosphere, you can get outside of the craft and work on it if need be, on maintenance or repair. So that's Gemini. And then the Apollo was 3 astronauts. 2 of the astronauts would get in the lunar module and land on the moon. The 3rd would stay in orbit around the moon and prepare for the rendezvous with the lunar module as it came back up into orbit. So they went on Apollo 11 safely onto the moon and back. And one of my jobs was, since I worked on the optical systems, one of my jobs was to make sure that they used the optics properly and that they used the optics properly and that they did the right star sightings for navigation. And they also sighted landmarks. So now when we went from Earth orbit to the moon orbit, toward the moon, it was 24,200 miles per hour to boost from Earth orbit into an orbit toward the moon. So the pathway was all figured out. But what happened was things would drift, there'd be little errors. So the astronauts had to make corrections. And so they made corrections with the guidance and navigation system on the craft. they didn't require anybody else. They could do the whole job by themselves. And when they got behind the moon and ready to come back to Earth, it was all self-contained guidance and navigation. So it was all by itself. Nobody else was needed. And that was the major thing, get home without the help of anybody else. So on July 20th, they walked on the moon. They had lots of cameras. So you wonder how you could see all this stuff. There were lots of cameras inside of the craft and outside of the craft, the lunar module, to document what happened. And so they spent 23 hours on the moon. And today, we owe the work that they and other astronauts did, that we can measure the distance between the Earth and the moon to within less than an inch. So we had these retroreflectors, and this is a laser. This is a laser, see, a laser beam that we put on the wall over there. So what happens is the telescopes on Earth can shoot a laser beam up to the moon, and there's retroreflectors that were left there by the astronauts, 3 by the United States, 1 by the Russians in an unmanned landing. So we today are still measuring the distance between the Earth and the moon, and that's a major legacy because the moon is slipping away from Earth. And that slipping away can affect the tides and the seasons. Excuse me. So that is a major legacy and a very important one that has to be tracked to make sure that it doesn't keep growing. The error of the moon slipping away from Earth does not keep growing. Okay, so NASA was not a great sales organization. So they brought back rocks from the moon, and everybody said they spent all the billions of dollars to bring back rocks. Not a very good idea, but I'll show you the real legacies of Apollo at the end of the presentation. So we were there 23 hours. Okay, next. So there they are. There's Armstrong, Neil Armstrong, he was the head of the mission, and Buzz Aldrin. These two men went onto the moon, and there's Michael Collins. He stayed in the command module, keeping the craft ready for the rendezvous when they came back up from the moon. So Neil Armstrong passed away last year. Okay, now we're getting into some of the things that I did. And I didn't do any of this by myself. It took a lot of people, and I just had a niche in the optics, in the telescopes, and the sextants, and so that was my job to help integrate it all with the guidance and navigation system. But here's how it helped. This rocket is on that big track there. That's the full-size rocket. And look at that building right there with all the cars, trucks and cars are all parked there. See that building? That gives you an idea how big that is. That's end to end the size of a football field, that rocket. So, 316 feet, something like that. Now, well, what do I have to do? This came out from the launch building where it was stacked. And we had the lunar module was right inside there. And my boss said, if something goes wrong before flight, we want you, Jim, to design a test to sight on the stars and make sure that the new guidance system we put in works properly. So that was my job. Now, if it didn't work, if my test design didn't work, they would have to take that whole tractor all the way back to the vertical assembly building, which is 3.5 miles away, and unstack the whole missile. So, as you can imagine, that was a very tall order for me to look inside. I was in the gantry, and to go and look inside there and make an estimation of whether we could do that design for nighttime star sightings, that we could transfer the line of sight. And my engineering judgment was that we could. So I called my boss up in Cambridge, and I said, you know, I think we can do that, but I need 3 days to prove it. He says, don't bother, Jim, just come on back home. So I never got to prove it, that we could do it. And we never had to use it. And believe me, every time we got ready to launch, my heart was going like this because I didn't want to have to prove that. And that was one of my contributions. Go ahead. Okay, this gives you an idea how big that rocket really is, because those are all trucks and trailers. There's vans like we use around here, and the vans down there, so that gives you an idea. And that's how it got in there to where the stowed rocket was, the lunar module was, and that's the one that I was working on. I also work on the command module, which is up here, the command module guidance and navigation system. So this picture, this is the guidance console to give you an idea how big it is. Now, this guidance console had a computer, and NASA said, how big do you need to have the computer? And we asked them, well, how big did you allow for? And they said a cubic foot. A cubic foot is a big computer. And how smart was the computer? It was about as smart as not even a cell phone. I mean, it was dumb, but it was very, very reliable. So we had a computer, 1 cubic foot, and it drew about 60 watts of power, and that was a lot of power for running the mission. So that was a lot of my work was in the laboratory. There's the optical system, and there was a guidance platform. And so a lot of my work was in the laboratory, simulating the flight and simulating star sightings. And we actually took the whole thing up on the roof at Draper Lab in Cambridge. Took it up on the roof and sighted real stars also. And one of my other contributions was an automatic star tracker. And one of my papers went into that. In 1968, I wrote that paper. And that, in the work that we're doing for Mars and beyond, that star tracker is being incorporated into the guidance system. So that was one of the legacies. So that's the kind of work that I did as a grunt engineer. I wasn't a big manager or anything like that, but I had to make things work, and that's what we paid me for. So there's a Saturn V rocket, and it's staging, 3 stages. And how heavy was it? Well, it was about 6.7 million pounds. And how powerful was it? It was powerful to do 84, as I was saying, 84 Hoover dams, or light up all of New York City with these rockets. And so it was about over 7 million pounds of thrust. Now, when you see the little rockets like this one, if you put this on the ground and you fired it, it would go zip, it would go up in the air a couple hundred feet. Well, this rocket was so heavy that when it took off, it took 11 seconds for the bottom of the rocket to reach the top of the gantry. So it took 11 seconds to get started. And the noise was huge, and we'll give you an idea about that. So it's about a football field long, and there's 7.5 million pounds of thrust, liquid hydrogen and liquid oxygen, 3 million parts. So what's the chance that the astronauts are going to use those 3 million parts and they're all going to work right? What's the chance? The chance is 1 in 10. So 1 in 10, they would be a success. Turned out that all of them were successful flights. All of them. That was up to, from flight number 11, was the first manned, all the way up through flight number 17. And then we had those prior flights that I talked about. So there was big arguments all over the place. Should we have fully automatic operations with the crew, just along for the ride? Or should we have ground-based or pilot-based decisions? So the pilot's going to run the show, or is the ground-based guidance folks going to run the show? So it turned out that we did have TV on board, and we did have lots of self-contained guidance and navigation. So let's see what happened. Okay, that building that I showed, that's where people were. See the hundreds of people in there? That's only one of the buildings. All over the world, there were radar stations. All over the world, there were places that supported the mission. So this one is the building I showed you at Kennedy Space Center. So Houston was the major controller for manned spaceflight, and that's where I ended up helping out during the Apollo 11 flight. And then I helped out also in Cambridge after Apollo 11 and Apollo 12. I worked at Cambridge, and I was on alert in case we were needed for problems, and we did have optics problems and so forth. Go ahead. So there it goes. There it goes. Now, some people think that that's a person standing there. That's not a person standing there. He was a cinder block. He would not make it. Now, how do you think they made that rocket go up without burning up the whole gantry and burning up the whole launch platform? This is only a pop quiz, but anybody guess how he did it?
Water.
And spray water.
Water.
Very good.
Yeah.
Very good. It turned it into steam. And so it was steam, this steam that came up was really a lot colder than the rocket. So that's how they kept the whole thing from burning up. Okay, there's the rocket from above. Now, the astronauts are right in the command module. And this is actually a little rocket. So what happened is, if the rocket flew up underneath, and we had a lot of those things happen on non-manned flights, if it blew up, they could break away from the rocket and send this thing with the command module and the astronauts into the ocean, and they would be picked up by an aircraft carrier. They would be saved, even though the rocket had burned up. So that's what that launch escape power is all about. They never have to use it. The mission always worked. Okay, that's the command service module. Now, Apollo 13, people ask me about that all the time. Apollo 13, there was a pressure transducer that failed and blew up part of the command module, and not the command module, but the rocket. And the command module became inoperable for the most part. They didn't have enough energy to run the command module. And fortunately, they had not landed on the moon, and the lunar module, which hooked right in here, the lunar module was still operable. So they had the lunar module, and its rocket was used as a taxi to bring the astronauts safely home on Apollo 13. They asked me a life and death question about whether the guidance system would work, because normally it had to be warmed up for quite a few hours. And they said, well, Jim, we don't have those hours and we don't have that much energy. You think it'll work right? Yes. That was my best guess, was yes. And the systems did work. And the command module, you could actually steer it. The astronaut had a joystick and he could steer it, and he could make it go long in the atmosphere, or he could make it come in steep. Now, when they hit the Earth atmosphere from 240,000 miles away, when they hit that atmosphere, it was going 36,000 feet per second. So even the atmosphere was a rock hard thing to hit that. It was like concrete. And so the astronauts could steer it up or down a little bit. And if they went too steep, it would kill the astronauts by making too many Gs. If they went too shallow, it would skip out of the atmosphere and they would be lost in space. They would not have enough energy to get back home. So it was very crucial of exactly the angle of attack into the atmosphere. And that's where all the guidance and navigation came, and all the accuracy was required to keep from losing the astronauts. Now, how did you get locked up against your seat? Well, the gravity force was like 8 times. So the astronaut weighed 8 times his normal weight when they hit that atmosphere. So it was pretty hard to do anything but steer it a little bit with the hand. Now here's the moon, right here. This is the moon, and it's only 8 miles to the horizon. And there's the Earth. Now the Earth, you only see half of it because the sun only lights half the Earth at a time. So, now here's the lunar module as it was getting ready for landing. So you see these little rods down here? These rods on the landing pads, those are, when the lunar module lands, you got to turn the engines off, because if the engines keep going, it'll tip over the spacecraft. So one of my jobs was, when they landed, was immediately to do some star sightings to get them ready to take off, because we didn't know if the whole thing was going to tip over or not. So that's what those are. And here's where life and death became right up into your face, because they only had a short, see, they have to land somewhere. This is not the craters where they landed, but it was very similar to it. So they were steering the lunar module, and when they ended up landing, they only had 22 seconds of fuel left. And that 22 seconds of fuel was the difference between crashing into the moon or landing softly on the moon. And they landed softly. And it didn't tip over. It was level enough that it would not tip over and not be launchable. So it was launchable, and we determined that right away. So the job of the telescope that I worked on was to make sure that they could launch right away if they had to. just to give you an idea of what it sounded like.
Down, 2.5.
3 days later.
2.5 down. 6 down. 4 forward. 4 forward. This is the line roll. 6.5. Contact light. Okay, engine stop. So it's just, tranquility base here. The engine has landed. You're going tranquility. We copy you on the ground. You got a bunch of guys about to turn for it. We're breathing again. Thanks a lot.
So this is where
Okay, there we go. You're coming down the water now. At the foot of the water, the land footprints are only, interested in the surface about, 1 or 2 inches. They're going to step off the land. That's 1 small step for man,
There's his foot.
1 giant leap for mankind.
One giant step for mankind.
90 feet, please.
There's the buzzer. This is not Apollo 11. This is one of the latest ones. That's so they could explore more. And the moon is, the mass is 1/8 of the Earth. So the idea is you can jump it real high and far. And there it goes. See it pop up in the air? That's the lunar module coming back home.
Oh my God.
Now, if it turned over upside down, it would be stable in that environment. They had balloons that would force it to turn back upright. And so it got it upright. So here's what happened. My boss, Doc Draper, and all the big wheels from NASA were all having a couple of drinks to celebrate. And Doc Draper gave me his badge. He sent one of the fellows over to give me his badge. And I didn't know why. I mean, I had my badge. I was 31 years old and he was in his 60s. And they said, well, you can go in the back room where all the astronauts are congregated and all the big wheels from industry are congregated. You can go in that back room and talk to them and introduce yourself. So I go in there, I'm this young buck, and there's Doc Draper's badge. And they're looking at me and trying to figure out, you know, you're no Doc Draper, we can tell you that. You know? So that's what happened. Now, for 45 years, I never knew why he gave me his badge. And I just realized why. And it was because we had a lot of trouble with the Lunar Module Telescope. And I'll show you, let's see. One of the pictures, oh, here it is. We just had a party in 2013 over at the lab, and we had a luncheon. And on top of here is a little cone. It's a little sunshade. Now you see how all that scattered light? Well, that's from the sun on the lunar surface. And that cone was my idea. It was a sunshade. And so when we were down at Kitt Peak National Observatory, my colleague and I had anticipated that we were going to have trouble with scattered light. And sure enough, you couldn't see any stars. It's a $15 million telescope, and you couldn't see any stars. It didn't work. So we were up there at Kitt Peak with a big searchlight simulating the sun on the lunar surface. And the telescope didn't work, 15 million bucks. So I was there for 10 days, we were trying to work it out. What happened was, my colleague and I realized that we were going to have that problem, and I had a sunshade with me. I had a sunshade with me that we used in the laboratory. And the astronauts were fiddling around, and they were making multi-million dollars changes in the spacecraft with shades and so forth. And I said, why not try this sunshade? And it worked like a charm. We could see all the stars we had to see. It was fantastic. It worked. So I go back to Cambridge. They wouldn't let me take the sunshade back. But I went back to Cambridge and I said to my boss, we're going to have to change the telescope design. And my boss said, we're not changing anything. We're not changing anything. We signed off, MIT signed off on that design, and that's what it's going to be. I said, well, you can't see any stars out of it. You know, you got to change the design to be able to see the stars. And that's what happened. That little sunshade cost about $500,000, and it saved $14.5 million. And I got recognized for changing it. And that $14.5 million came back to me as a pen and pencil set. So that was it, folks. You know, that was a key contribution that I made. You can also see on the internet one of the other contributions. All these Apollo miscellaneous and so forth. There's Gene saying, computer-aided inertial platform realignment in manned spaceflight. 1968 is when I gave that paper in California. That had a little funny thing too, because at that time I drank. So about 10 engineers were going to the Sprung Draper Lab, all the big wigs in my little grunt self, and I was given the paper. And so I was sitting at the bar and was watching the football game, and I got loaded. So I said, instead of going and finding where my colleagues were, I rented another room. Now my colleagues thought I'd never made it, that I never made it to that. They were all in some dormitory somewhere. And they thought I didn't make it there. But I popped up when it came time to give the paper. And so in 1968, I said we needed an automatic star tracker on the guidance system. And in 2014, in the summer, or in the spring, I told them we need it for Mars and beyond. So at the Science Museum, the guys that were working on that came along and they said, oh, you want a star tracker on there? Well, that's what we think you're going to need also. So my contribution became a legacy in the guidance system, and we proved with a package that it would work. So go toward the end there now where the legacy part is. Okay. So what you're trying to do with guidance is, where am I going? And navigation, where am I? And control, how do I get there? Well, as I said, it's all self-contained. So we had the optical system, we had a computer, and we had a guidance platform that could measure all the motions of the craft. And so that's what the guidance, navigation, and control is all about. And it all worked. And so how did we prove that we knew where we were going to go? Well, what happened was we did the star sightings and the landmark sightings over and over again as they were going to or from the moon. They did it over and over again and checked it against the deep space radar. The deep space radar said where we were and how fast we were going and so forth. And our guidance system said exactly the same thing, done with just one man and the system. So that's how we proved that we knew what we were doing. So there it is. That's what you need. You need that guy's brain, plus all the things that's stored in the computer. There's that 1 cubic foot computer right down there. And there's the guidance platform with all the instrumentation to measure the motions. You want to measure all the angles, and you want to measure all the speed. And you can do it all with one man, and you can do it with those pieces. And it works. So that's what the self-contained system looks like. And there's a radar for rendezvous and for landing as well. That was part of it, but we didn't contribute there. And there was also an abort guidance system that if our system didn't work, our system was going to work. But if it didn't work, you were able to use the abort guidance system. They never had to use it. So we're pretty happy about that. Now, so this talks about how you make all the measurements of the angles, and I won't bore you with that, but it's very, very tricky. And so that telescope that I was telling you about on the lunar module was a periscopic telescope. And I got this certificate of commendation from MIT and Doc Draper. That was Howard Johnson was president at the time of MIT, and his name was Howard Johnson, and he didn't sell ice cream. And Doc Draper, he was the greatest. People, all these engineers would come and try to say they needed a lot of people to do administration, and needed all this stuff. He says, we don't need any of that stuff. We're going to just do it our way with a bunch of engineers. And NASA was not happy about that, but it worked. And so it worked, and we only needed 23 stars for the total mission. And we were able to run the whole show with stored stars in the computer. So there it is. The sunshade wasn't there. See, there's the periscopic telescope with a little tiny sunshade. It didn't do anything. And there's the eyepiece. And it was all a manual system. So that's what I worked on at Colesman, was building and testing that part of the telescope with my hundreds of engineers. I didn't do this stuff by myself, believe me. Next. So there's the sunshade. That sunshade had razor blades inside of it. And those razor blades would baffle the sunlight. And so you could see the stars with that $500,000 sunshade right there. And so that was another one of my contributions. Now, if you guys are all much too young to have been there or seen it all when the moon landing. You mean you aren't too young?
No, I wasn't there.
Yes, you were.
Well, I wasn't saying hello as he came down.
Well, see that little blue dot right there? That's the Earth. Now this is Buzz Aldrin getting his picture taken, and that's his face mask.
Yeah.
Now, anyone who was on the Earth and looking up when they were landing on the moon and taking that picture had his image in that little blue dot. So that's where we all contributed. There's the picture of Armstrong being reflected back, and there's the lunar module. And these spacesuits worked. If you get a hole in the spacesuit, you can perish very fast. And these multi-million-dollar spacesuits work. And we're going to need those to go to Mars, that's for sure. So there's astronaut. Now you can get an idea of the size. So this is the part that goes up, and this is a launch platform. So when you saw that thing pop up in the air, from the moon, it's just that half that did it. So there's a crazy looking thing. Anybody know why it doesn't have an aerodynamic shape? Like this is an aerodynamic shape on the command module.
No air.
No air. Exactly. Judy, you get an egg. All right. Give her a cookie. So that's it. There's no air. And there's a rendezvous radar and a landing radar. So when they came back up in, they had to get in the right trajectory, the right path to intersect with the command module that was orbiting. Then they transferred from the lunar module into the command module. And then when they got behind the moon, they fired the rockets to come out of lunar orbit and back into Earth orbit and fall 240,000 miles to the ocean. And there they are. They have to get debugged because nobody knew if there was going to be microbes that came with them from the moon and were dangerous. So they had to get all scrubbed up. You can see how burned up the command module is. These things helped it float. So they were safely landed in the ocean. Actually, at one of the flights, they missed the carrier by 100 miles. And but 100 miles, when you've come all that way, they were able to have the safety of the helicopters pick them up. So that, it's hard to see, but that's all black. That's all ablated. It didn't boil. It went into a gas. And so that's what saved them. And look how black it is up there. There's the balloons that if they turned upside down when they landed, the balloons would force them to come back upright. So there's the astronauts inside a big trailer, and they had to stay there for a week because nobody knew if there was any bugs that would kill people. Here's the advanced guidance system. I worked on this. So a lot of us went to work on the advanced guidance system after Apollo. And so it's actually being used. And this is a rocket sled that I worked on down in New Mexico. The advanced guidance system was located in there, and we sent it down a track about 5 miles at 1,200 feet per second, which is about the speed of a bullet. So we did a lot of advanced work afterwards. So there we go. This orbital navigation software, we use that in the space station that's going around. So we saved a whole new design by using the stuff that was in the Apollo guidance and navigation system. There's that Earth-Moon distance measurement that goes on today. And it's very important. And then the moon science is the rocks and what it's made of. There's the commercial airline. So when you're flying across the ocean at night, across the Pacific or the Atlantic, they have guidance systems that help you immeasurably. One of my friends that I went to college with, he said, "Thanks, Jim." He says, all I had to do was put in a couple of buttons and the thing would fly itself exactly. And it would save a lot of fuel and would save a lot of lives because nobody got lost. And then space rendezvous. Now we're able to rendezvous with asteroids. And you might have heard in the newspapers, the asteroids can be a lot of trouble for 1,500 people, 1,500 Russians were affected by an asteroid coming in. And so it can be big trouble. So how much did it cost? People, as I say, NASA couldn't sell it. They were not good at selling it. How much did it cost? About $25 billion, roughly $156 billion in 2011 dollars. Second largest undertaking compared to the Panama Canal. So it was a huge victory for the United States. And the return on investment, NASA tells us, is $7 for each dollar expended. So it's a huge, valuable bunch of work that was done for the folks in the Apollo program. Now, in 1967, how many people worked on Apollo? 370,000 people. And they all went their separate ways after Apollo, and they went into advanced systems, they went into defensive systems, they went back to their contractor companies, and all these legacies were very, very valuable. So the turning point in American history is this. A grunt engineer like myself comes up, approaches the manager and says, I have an advanced project, and it's a wonderful project, and it's going to save the world. And the manager, this is all before Apollo, the manager says, your advancement is impossible, it can't be done. So after Apollo, the manager replies, if we can go to the moon, we can do anything. We can do anything. Anything is possible. We'll get together a project team, and we'll find a big bucket of money and support your research and development proposal. And that's the end of my presentation, and I'll address your questions, if you have any questions.